I'm really, really thrilled to see such great turnout. We have a number of people online as well. So this is the first in a seminar series for the Center for Climate Change and Health. One of the things that we were thinking about in putting together this seminar series is that we recognize that a lot of the solutions that are going to be really important for thinking about climate resilience, and particularly thinking about climate resilience for public health, are not necessarily going to come from within public health. So we really wanted to have people from around the university who are working on topics that are really closely related to this. And as I was saying, doing real things and doing really applied work. So I'm very, very happy that we have Professor Daniele Malomo, who directs the Struct Lab, which is in civil engineering, and we were just chatting beforehand. Breaks a lot of things.
Yes, I'll show you a lot of explosions or something like that. We'll have fun.
And so, does a lot of different work related to like earthquake prevention, designing buildings for earthquake prevention. Also thinking about how to design buildings for the future that are going to be more climate resilient, but also thinking about what do we do for these buildings that exist now? How do we make those more climate resilient? So I'm going to turn it over to him, and we're really excited to hear your talk.
Yeah, likewise. Well, thank you all for coming. Thank you, Jill. Let's see if we can go in presentation mode. Let's sort it out. Let's see. Maybe I should, hopefully share my screen, share, and then presentation mode. I hope everyone in the audience online will be seeing this. So hello everyone. You'll see it's pretty applied stuff that we do. So we like to call ourselves, I'm an engineer. I like to call myself an applied scientist, but scientist just is not the right word to use. You'll see we do a number of things in my lab, including breaking things as part of the process. We do it for science. It's great for stress relief. Other things. So this is let's see. Does it? Usually it's like this. No, it never works
when you actually use it.
When you actually use it. Now it does work. So we're a big lab. We're a big team. There are a number of postdocs and PhD students that help me out. We are right there in McDonald Engineering. It's quite a big lab. And we do a lot of things that are very practical, so mostly experimental. We do some numerical things. And really most of our research revolves, well, as my students say, we have asked money to everyone. And so our projects are pretty expensive, very applied, if you want. And what we do essentially is we work a lot on existing buildings and on climate change adapted solutions for designing new ones. My philosophy is always like, if you build a building today, tomorrow is an existing building. So it's really like a problem that relates back to, to preservation engineering, as I would like to call it. So we use, we are focusing on different materials from a structural engineering viewpoint, masonry, concrete, timber, steel, you name it. Our specialization is mostly masonry, and Montreal in general is great for that. I'm European. I'm from Italy originally, so masonry has always been sort of my main interest. And Eastern Canada, we'll see it's an interesting place for that. We do a bunch of tests, mechanical, environmental. The main goal is to try and preserve buildings that already exist, to reuse them, and we will go through a few numbers that is one way of making them sustainable as well. It's a big word, but still. So building preservation, reuse, and climate adaptation are sort of the keywords of this presentation. I will go through a little bit of background because most of you are not maybe familiar with the terms and things that we do. And I would like to make the link with climate change and sustainability as well, that it's not that obvious if you're not in the field. And then I'll show you a few projects with a few destruction, explosions, and cracks, I promise. So we use well, in the main domain of structural engineering, we also do seismic, which is a subfield. So anything that pertains to repair and retrofit is of interest to us. So just a few figures. I mean, you're much more expert than I am in terms of statistics and number like this. Usually we say that 80% of the GHG emissions are due to the built environment, or at least related to construction and so. In Canada, we have a problem with climate change. I'm not the first one, to tell you that for sure. But in general, from my perspective, is the warmer temperatures and the sort of alterate rainfall that causes most of the issues that I'm trying to address. And of course, when you jump from snow to water, then you have all sort of problems in buildings. And in general, this leads to certain consequences for the built environment, in the sense that you have a building that deteriorates faster because initially has been built for sort of addressing different environmental conditions. No? So climate change, but then building change as well, and so it's not always a good match. And in general, the built environment is one of the most critical sectors for climate change. That's for sure, and it's going to cost a lot of money in the next few years. Anyway, this is the some of the background, and we have mentioned some of the issues. People in governments and groups try to address those issues sometimes as fast as possible, which is not always the best thing to do. So you may have heard and you may have seen in Montreal as well, a lot of mass timber, a lot of solutions, prefabrication. I have my own ideas on that, and I'll share that with you, those with you later. But in general, just to give you a few examples, the National Building Code of Canada, especially the one that is focused on energy, is increasingly sort of setting higher standards for sustainability, which is good. Don't get me wrong, but if it's rushed as a response, you risk, of finding yourself using what are called advanced materials, so very expensive, very hard to fabricate, very costly, and seldom affordable as a solution. An example, again, on very practical stuff. If you look at the national housing strategy, which has been released right before Trudeau sort of ended his mandate. This is very fresh, 2025, really. So we all know that we have an housing problem, no? And the one main problem in terms of housing is that we need to build more. At least this is one of the solutions that is sort of out there. Nothing in the strategy that has been presented sort of addresses building reuse, and that was very concerning to me. But if you look at the solutions, the rushed response that has been sort of put out there, one of the main key points was to use prefabricated homes, so homes that are easy to fabricate, modular, and so on and so forth. This is not really new, so it's the history that sort of goes in circles. So whenever you have a rush response to try and build green, right, then you may end up with problems. That's my sort of my thought on that. And if you look at this drawing, this is 1940 or something. So. And CMHC, Canadian Housing and Mortgage Corporation, did came up with these solutions, 70 years ago. So it seems like we're going in circle. At least in my sector, this is the feeling that I have. Whenever you look at building reuse, it's going to take a little more time. But in the long term, you're going to get back. You're going to be more towards carbon. I wouldn't say carbon neutral, but definitely carbon conscious. So if you look at the existing and the new buildings in a changing climate, now I have two examples here. So Montreal, it's a perfect example of that. You have downtown very modern, then you have old Montreal very old. So if you look at this, for instance, this picture right here, it's clear that buildings change and their uses changes, throughout history, even 50 years. In general, I like to think about existing or something that already there, as the greenest solution ever. And it's not just me; the data, back that up. This is a famous line from Carlo Elefante, an architect, a few years ago. But on this, on this line, and that is why we're so interested into this. These buildings that are already there, they've been sort of winning the challenges of time. So there must be a reason why they're still standing, right? Truth is, it's not so simple to try and refurbish them, renovate them, and reuse. Most of them, especially seismically, they are not necessarily up to code. So that's definitely a problem. So to me, there is always a conflict. As an engineer, as a preservation engineer, would like to keep them. And this is what we do as researchers to try and bridge the gap. But there are problems, issues, and barriers to that. Changing climate changes building. Of course, you need to sort of put things up to code and adapt continuously to the climate or the local climate that you have. And then there's this major barrier. So National Building Code is what governs the way we build. And if you change use of a given building, or if you do a major renovation, this building needs to perform like a new one. Okay, so that is one major barrier. And that is why you see oftentimes very invasive interventions in older buildings. It's because we need to meet whenever we change the use or we do major renovation, existing, new codes, essentially. Even for a building 100 years ago, it needs to perform like a new one. So that's a barrier. And then if you look at this assembly of different materials, definitely there's the potential to take, even if you end up demolishing it, taking up some bricks here and there, concrete, steel, and reuse these things, or deconstructing. So you might not know, but most of the uses for bricks nowadays, and we have a lot in Montreal and in Eastern Canada, whenever they're deconstructed, they are either, they either go in the landfill or they are crushed, and we make tennis courts with that color. So it's not really, there are not a lot of tennis courts around, so most of those go into the landfill. So some of our work looks at sort of reusing this material and try to decrease our carbon footprint in there. Everything that we do needs to be affordable, otherwise nobody will use it. And that is one of my main arguments, right? If you want to have an impact and you want to have it sooner than later, you need to make something that people can actually use. No, otherwise everyone can use hydrogel or whatever, very high sort of performance, high cost things to do to improve building performance. For new buildings, and this is other part of our research, of course, you need to design for the climate that you have locally. So a solution that is very sort of performing very well in Europe might not perform at all here in Quebec or in other regions, right? So every approach needs to be local enough. And if that's something that we believe in, we need to understand what's the context, the environmental context, but also what kind of materials are available here. So timber here is different from timber on the West Coast, for sure. So again, we need to adapt to the local climate. One of the things that we will see together in this presentation is that insulation, especially passive one, is really, at least in our perspective, the key. So, and we'll see why, but in general, using low cost ways to sort of augment the thermal performance of your building. Whenever you have a local context, so using local materials will decrease your carbon footprint dramatically, right? And there are ways of doing that, and we're not even talking about crazy, things that you need to do. So there are ways of building locally, right? So low cost versus advanced. That's the battle that I'm conducting. Low cost means that your solution needs to be engineered, needs to be tested, and is a longer process. Advanced, it's easier because you're using higher performance material in general. It's unfortunately not very affordable. Construct to deconstruct, that is another thing that we're looking at. So whenever you're constructing a new building, do it with the you need to realize the fact that one day, that building will need to be deconstructed. So just a question, I ask this question at every lecture that I do similar to this one. So how many years do you think that, for instance, a residential building should last in terms of lifespan? So from its erection, its construction, towards, I wouldn't say demolition, but end of use. What do you think? Number of years?
100.
100.
75.
75, that's a good guess. Okay, well, we got some good numbers. In general, it's 50. So we design buildings that in general, standard buildings should last 50 years. None of my house included. No, it's been built in 1945. So definitely has passed that sort of lifespan. But in general, if you build with the perception that your building is going to last 50 years, then for sure this becomes key. Construct to deconstruct or construct to maintain. You need to maintain your building. We'll touch upon these points, but it's always interesting to see, that there is always the perception that our buildings will last forever, and it's not necessarily what's going on. Right? Concept of smart, we'll talk about it later, but every now it needs to have sensors into it, and it needs to communicate wireless. Our research, is based on things that are a little bit more traditional, and this is, my dilemma as a structural engineer. So if you think about a building that is already existing, and you think that you would like to keep it or adapt it, to climate change and to the new natural hazards or man-made hazards, there is always this dichotomy, this duality that is sort of it's really an internal struggle. So if I want to sort of extend the lifespan of my building, it's not only great from it's great from a lot of perspective, but essentially from my perspective, I'm increasing its lifespan. Hence, I'm increasing its risk of being exposed to threats. Right. So this is the perfect image to me. Right. If the shark is your hazard, think about it as in terms of earthquake engineering perspective, it could be your ground motion. And then your exposure. So a number of buildings that are out there, the more they are, the more your building stock is exposed. That's why Montreal, it has a low hazard, but a lot of exposure, a lot of vulnerability of the local building stock. So the risk is actually very high. So that is what we're maximizing when we're trying to extend the useful lifespan of the building. So we need to realize that there is an enhanced risk for that. So if you look at, again, this is just an example, jumping into the earthquake engineering side of it. Now, the West Coast, we all know that it's seismically active. Here, we're less seismically active, but because of this linear addition the risk in the Montreal area, Ottawa area, it's actually very high. And so that is why we have some challenges in there to try and reuse buildings, to try and build to deconstruct all these techniques or these workarounds that we're trying to play. There are challenges attached to it. Right, so an existing building are going measure renovations must perform as a new one, which is one of the sort of current barriers. Other barriers to climate change adaptation and preservation. Most of our norms, so everything that pertains provincial codes or national building codes, most of those are conceived for new buildings. It is very, very little. There are about 12 pages in the National Building Code on existing buildings. So there is very little. Lack of engineering guidelines. So there are no guidelines in Canada. There are guidelines in US. There are guidelines in Europe and in other countries. But those buildings are different from ours, right? So part of our research is try and foster a collaboration with industry and get those standards done on our buildings right here with our climate. And the same applies to building adaptation. So we have been talking about the lifespan of a building, 50 years, 100 years, and so on and so forth. There is the perception that materials are durable, to infinite. They will never sort of perish. They will. And so maintenance is another thing that it's very important. Most of our engineers, even if they will never admit it, they have very little knowledge of what's going on in existing buildings. There are a lot of examples, but there is a lack of sort of knowledge in terms of the materials themselves, how they would behave. Most of our engineers do rely on material testing data that have been obtained in Europe, in New Zealand, in America. So it's in the US. So it's different. And so our assessment it's flawed. And they will end up using very conservative value for those assessments. The more your assessment, structurally speaking, is conservative, the more material you will use for retrofitting, right? I'll talk about knowledge factors later on, but that's what it is. In my unit, so I'm from civil engineering, there is one course on existing buildings, and that's mine, 600 level. In Canada, only 2% of the lecture hours that we have in civil engineering is on existing, and virtually none on climate change adaptation. So there is something, our engineers, they don't know things because we don't teach them, right? And so that's a little bit of a loop in there. When engineers lack confidence, they end up, overshooting and over-designing. So it always sort of gets back to the knowledge factor. So the less we know, the more we are scared, and the more we over-design things. The more we over-design, the more material we end up using, the more demolitions we're gonna sort of perform. And this is, more or less what happens. So I like these pictures because this is how an engineer think about the life cycle of a building, or at least the damage or the risk that a given building can undergo during its lifespan. So this is called the Joe bar. Now, the Joe bar is very important, very it's a milestone in earthquake engineering. Whenever you have a building in its lifespan, these are the different types of damage limit states that it can encounter. So the building after an event, a settlement, an earthquake, strong wind, whatever that is, can remain operational, right? Immediately occupancy, the next damage level, so it can still be sort of right after the damage. You can still enter the building, use it, but damage is evident. Life safety, whenever a building is unsafe, right? Or a building that is able to sustain life safety. It means that if the roof collapse, right, there is a sort of people inside are in danger, right? Collapse prevention. So a building that is, that reaches that limit state is collapsing. And so if to design for that limit state, you need to make sure that the building doesn't necessarily collapse during an event. So these are all sort of stricter requirements as you go here. So if you have a natural hazard problem or risk, right? If your building remains operational, it's an example, for instance, of a hospital. A hospital after an event needs to suffer very limited damage, needs to continue working. Usually for our residential buildings, life safety is the target value. It's the target value for our design. So if I retrofit the building, if I repair a building, I need to sort of fix my target performance. Usually it depends, but we're around here. So my design should make sure that the people inside don't get injured, don't die. It makes sense, but this sort of this target, it's hard to achieve, especially for an older building. But I'll give you a few examples. But this is how a structural engineering mind works. And this is what I like about US guidelines for existing buildings. So whenever we design a building, well, we know the materials that we're using, But if you encounter an existing one, you don't know what's going on. If you don't do testing, if you don't know what's going on in your construction details, you need to overshoot your design. So, for instance, if you don't do testing, you need to increase or to decrease in that case the mechanical properties of that specific material by 25%, which means that you're already designing by 25%. So the less you know, the more you'll overshoot, and the more material and more carbon footprint you'll have. So a lot of our research is really to gain the knowledge, to gather the knowledge on materials and construction system in Eastern Canada, mostly. And I'll explain why. These are the direct consequence of knowing not enough, let's say, of having a lack of knowledge. So this is in the UK, but it's very applicable to a lot of sites in Montreal, Toronto, and all over the places in North America. And I'll give you an example in Montreal, in the Plateau area. Whenever less, you demolish, right? Of course, there are restrictions, a lot on the facades, for instance, because cities, municipalities like to keep sort of the aesthetics of it intact, no? But this is what happens. So this is for a number of reasons, this is absurd, and of course, all the material that is on this side, it's basically discarded and go to waste. No? An example in Montreal, again in the Plateau area. So if you are familiar between Saint-Denis and Mont-Royal, so it's right there. So this is 2015, and I lived right across the street. So I made some of these photos, and this was a really sort of interesting sort of case study for me. So 2015, this is a typical triplex in Montreal. So you have, your stone outside is made of wood inside, very typical. So what happens, there was a commercial place here, and then a residential of the upper stories. So in these 3 years, nothing has really changed, apart from the fact that this commercial shop has been closed. That was the main change there. And so they decided to renovate the place, or at least to change its use, probably because this shop has been closed. So what they did, they tried to address this by essentially by, well, you will see, but they have demolished everything that was inside and just left the shell. And that was because the city of Montreal really dictates to maintain the inside. So then there is another question. So first mistake, right? To demolish everything that is inside, but then how you're going to replace what was there? You have a few alternatives. And so if an engineer, this is the current state, so there's a McDonald's in there, looks nice from outside, looks very similar to the initial one, but the carbon footprint of this new building is completely different. So I'll show you what's going on inside, right? And this is a surprise if you don't know what's going on. So this was the previous state, so nice masonry walls and so on and so forth. And demolished everything inside. This is one side of it. Other side, same thing, right? There was really just the shell outside. But then they came up with this system, which was basically a reinforced concrete building inside the old building. So this is to me is a clear demonstration of an engineer or an architect who has designed this. They didn't trust the original system, the original floors, the original columns, the original posts. So they didn't know really what was going on, and so they decided to just get rid of it and build new, right? Lack of knowledge. Right. This is one of the main reasons that why this happens. And it happens a lot. And there's a lot of sort of discussion on how to address this, not only in Canada. So globally, this is a big problem. This is something that makes me laugh a lot. I mean, it's a little bit sad, but still. Imagine you're intervening on hundreds of bridges. This is in the UK with concrete, right? And then you had to reverse the intervention. So imagine how much material have you wasted, and imagine how much time have you wasted. Lots of money. So this is just an example, but there are others. So if you look at what's going on in Montreal or in Canada, Eastern Canada is very special. So now we live in Montreal, so we know that our buildings oftentimes they're older than others, right? Especially in other regions. If you look at our building stock, Quebec, Ontario, when there is most of the population nationally, 60% of those have been built before 1980, which means that most of them are reaching their nominal lifespan, right? So we have quite an old building stock. Most of those are residential. So most of those are residential, and we will see that thermal efficiency is going to be a big problem sustainability-wise, and even from a climate change adaptation standpoint. Most of those are detached houses. We want space, and that is why most of our houses are detached houses. And most of those have materials that we thought were invincible. So these are some advertisements for concrete, right? We thought the concrete would last forever. Instead, unfortunately, the rebars to corrode, cracking happens. And so unfortunately, all our foundations will crack at some point. And other things that are sort of pertaining the Canadian building stock, just a few figures. So all these different colors pertain to different materials. Our building stock in Canada is mostly like timber, which is in green. And then you have your concrete in gray, residential, commercial, industrial, and so on and so forth. So at the first glance, if you look at this, for sure for residential, your main issue is like timber. That's our building system. But then the more you go towards larger buildings, like governmental, educational buildings, commercial, then masonry sort of stands out a bit. It's in red, right? And the same applies for concrete. So there is a little bit of variation, but for larger buildings, we do use a stiffer materials. So in general, if you look at residential buildings, space heating is the one that has the largest amount of GHG emissions. So that is really one of the problems. So that is why I said before, insulation, passive insulation from a climate change sustainability perspective is key. And since that's the key, you would like your envelope not to crack, or at least to crack the least, so that that also everything is tied, mechanical damage to sort of thermal efficiency. So in general, whenever you want to sort of start and reuse a building, there are a lot of challenges. We've mentioned some of those. The way we think about reusing and making an impact in the next, say, 10 to 20 years, because we don't have a lot of time, right? Most of our agencies would like to have high risk, high research, being performed, fine. But if you want to make an impact at the regional scale, right, you need to identify clusters of buildings that will give you sort of the better gain in the fastest period, in the shorter period. So what we have identified is Eastern Canada as a zone where population is the largest in the country, 60%. And then there are this typology, which is called reinforced masonry, right? So this is our special. So maybe we're a little biased, but still, most of these buildings are, the non-residential buildings. It's very difficult to retrofit and repair, private buildings because it's the owner that then has, the power to decide. For non-residential building, commercial, governmental, and so there is usually building managers that manage that. So it's easier to influence those policies. Of course, those are the buildings that they are most inefficient. Reinforced masonry, it's older usually, and the envelope is not well sort of thermally insulated. Eastern Canada, it's a low to moderate seismicity area. So it makes sense to retrofit those. In the West Coast, you won't see a lot of those. Most of those are already collapsed. So in Eastern Canada, they do have a little bit of a larger lifespan because, of course, the seismic threat is a little lower. And of course, there is a lot of pressure, from the government and other entities to renovate, to maintain, of course, and that's why we need affordable solutions. So that is our sort of ideas in terms of what kind of building you got to target in what area, and most of our research revolves around these two things. So if you look at, again, the big picture, what's going on in Canada-wise, and you can focus on the color. So whenever this sort of pertains the year in which buildings have been constructed, and if you link that to the evolution of the building code from a seismic perspective, you will see that you'll have some buildings that are pre-code, before 1941, and then low code, mid code, and high code. So high code would be the buildings that we build today. Right? So buildings that seismically or structurally are, let's say, sound, right? Modern. All those buildings, LC, PC, pre-code, low code, all buildings that may have problems, if a natural hazard, in this case, earthquakes, will come. So there is quite a lot of that, right? And if you look at these trend lines, Quebec and Ontario, they're struggling a bit. Of course, they have the older building stock. So this is just to say, it's a localized problem, and it's a localized problem in certain regions. So my philosophy is you try to address that first for high impact, right? In a lower time span. So this is us having fun in buildings. Of course, you want to start with gathering the knowledge. And in Eastern Canada, or in Canada in general, there is virtually zero being done. So we don't know our masonry, how it performs. We don't know our timber, what are its properties. We take everything from outside, from abroad, most of it. So what we do, me and my research group, we literally go into buildings and take samples out. We bring those to our lab and we try to characterize them environmentally. So when we say environmentally, we say sort of the thermal properties of it, the porosity, all those sort of properties that then sort of link back to the environmental performance that they have. and also structural, how much load they can take in all directions, and so on and so forth. Here I'm showing in masonry, but we also have some cool stuff about timber. These are all buildings that are owned by the city of Montreal, and they're very proactive and supportive, and letting us access to those buildings, which is great. The beauty of focusing in Montreal historically has been a port of entry for most of our construction materials, initially from the UK and from Europe in general. Most of the stones, most of the bricks, if not sort of produced here, came from those countries. And Montreal really sort of was the first port of entry again, and then most of the material in Eastern Canada originally came from here. So if you start here, then you have a good shot. You have a good sort of overview of what's going on. So I was saying we crash stuff, we destroy stuff. Yes, we start from, these are very small things, but by the way, you will know probably some of these buildings from where these samples have been taken from. Compressive testing, this is mortar, this is stone, and these are masonry assemblies. So we call them triplet because there are 3 bricks. No? So this is the knowledge phase, gathering the knowledge of this build, of these materials. We do freeze and thaw a lot, freeze and thaw damage. We characterize them for how they would respond to local climate today, right? This is an example of our environmental durability testing. Most of the problems or issues that professionals have is with frost damage. And I'll show you just an example. This is a 1910 brick. This would be before the freeze and thaw test and after the freeze and thaw, just one cycle. So it disintegrates. And this would be what we call used brick. So this brick is 50 years old. So it's a baby. So essentially, what happens here, what is my point here? The tests that we have right now for characterizing these bricks are so aggressive. So what we do, we soak them into water, right? We soak them into water until they have absorbed all the water that they should. We leave them there, and then we perform 50 cycles of freeze and thaw, which if you think about the lifespan of this brick is nothing. Imagine how many freeze and thaw they have. But being saturated, being full of water, you test them. It's super harsh as a test. So if you look at this standard, it's written explicitly, do not use for used bricks. But there are no other standards for used bricks, right? So this is a big barrier for deconstruction, reuse, and so on and so forth. This brick will hardly pulverize like this because when it's in a wall, only the face, the outer shell, it's actually wet. So this is one barrier. How we aim to address these things, this is one of the projects I will tell you about. Modular panels, low cost, literally things that you can buy that by Home Depot. Every panel costs about $200. So I'll show you a few things. But this is a high-end project for us, was a very important project. This is in Caber. I'll show you a few things later, but it's one of the largest facilities in Canada for durability testing. And we're able to test a 3x3 meter wall, so big stuff. So just a quick overview of what we've been doing these years. Again, you might know these chimneys. This is a big landmark in Montreal, the Dixon chimneys, built in the 1950s, and now they're having problems with cracking. And the city would like to keep them, and try to build a center around those, which is really for certain communities that is a landmark. So they want to keep it. What was fun about this chimney is that we went on site, right? We're talking about this, and these are just sort of a normal cracking for chimneys. We went on site, and people were very concerned about the cracking that was happening in these chimneys. We were not really concerned, and the reason for that is that if you know how to read the building, the building will tell you what's going on. In this case, the chimney. This is a Coca-Cola can, but in general, if you imagine this being subject to its own gravity, it's pretty natural that if the deformation is like this, some vertical cracking will occur. And so if an engineer is not used to this type of forensic investigation, it's easy to say, well, let's just demolish them and sort of get rid of them. So we have been working with the city to sort of find solutions for this. What we've been finding out that seismically, this seemed to be sort of in pretty good shape, notwithstanding the crack. And that is, you learn that by being on site and by doing your analysis and so on and so forth. It was a lot of fun. And we're collaborating very well with the city. This is another city-owned building in Rue St. Patrick. This is presently used for they have cars that will remove snow that are stored there. There is a sort of a group of people that manage those. So we went there. We're trying to extract samples, got the full sort of point cloud of the building, and try to understand what the geometry was, and test them in our lab. right? So a lot of samples. This looks like sometimes I feel like Indiana Jones. You go on site, you take a lot of samples, and it's a lot of fun. But it's super important because these data don't exist, and if they don't exist, whenever you assess a building, it's very difficult to sort of proceed. And this also pertains to the new buildings. Now, whenever you build, for instance, a building that is close to maybe it's an extension of an existing one, you really need to make sure that the material that you're using is compatible to the old one, right? Otherwise, if you end up being too stiff, or less durable, then you have something that is not compatible. Something will crack here and there. So if you don't know what's going on with the older building, hardly you can manage to have buildings that are adapting to the changing climate and to the changing world we live in. Right? Example of things that have crashed. Surprisingly, these assemblies did perform very well, even though this is a 1914 building, right? And we do this with everything, with mortar, with this is just bricks and mortar, but there is more, timber and so on and so forth. And then when you study these buildings that are right there, the beauty of it is that you can sort of get the geometry, get the characterization, and reconstruct the samples in your lab, right? Which is what we're doing right now in the James Constructions lab. This is a 3 meter by 2.5 meter wall, so it's actually very big, right? And we've had masons from the city coming into our lab and constructing them. So we had to select bricks that were compatible with the existing one, mortar that was compatible with the existing one. We needed to add to the mortar almost 20% of sand to make it weaker, and still was much stronger than the existing one. I'll show you a few things. That's another problem. Existing materials, they're too strong for the older ones. So compatibility is always an issue. Right? So these are some of the walls, and it's basically this portion of the building that we are replicating. And we have many of those. So it's a big effort, and everything revolves around the knowledge. We're now doing this with the big walls to try and understand what would be the pattern of damage that you would get from a settlement in Montreal. It's important because if you crack the envelope, then thermally this building becomes inefficient. But it's better if you know what kind of damage you do expect from these actions. Other examples, you might know this building. This is right under the Jacques Cartier Bridge. It's a pumping station. It's called a Craig Pumping Station. So all these stones, this is an 1887 building, one of the first ones, or at least the last ones that we have from that era. This stone is very important in Montreal. It's called Montreal Grey Stone, and it's everywhere, including our campus. That's the Montreal Grey Stone. It's historical type of stone that here we have been using for everything. So my point is, if you try and characterize this, and you know that it's coming from the same quarries, right? These results will be valid for many other buildings. Chances are in Montreal. So again, you got to be selective with what you do in your studies. And we did all sort of tests to measure the tensile strength, the compressive strength, and so on and so forth. Other stuff, this was a residential building at Rouberry, which is in the Plateau area again. So why not to take a full wall and bring it to the lab? Again, the knowledge is key here. This is a 1910 building with 3 different leaves. So it's one brick, and one brick. So it's actually pretty big. We got 4 walls out of it and brought it to the lab. And then studying them, in different loading conditions, also in environmental. So most of these bricks, what happens in Montreal every day, whenever you disassemble this facade, you're allowed to reuse those bricks for the same facade. So it's very important to us to try and understand what are the conditions of the actual materials, to tell the contractor, to tell the engineer, yes, you can do it, more or less with the, you would be, approaching the thresholds for the code. So for this first project, and I'll try to to give you an overview of what's going on. We focused on some of the residential buildings that we have around here, duplex, triplex. And I don't know if you ever noticed, but especially here in Montreal and Ottawa, sometimes within the brick patterns, you have some timber elements inside. So people have been using this for attaching window frames or coats or something like that. It's actually a unique feature that no other buildings have in North America, and it makes these walls perform in much better size. So because there is a sliding plane. And so not knowing this, you would not know that these walls would have such a high deformation capacity. So that's why we extracted these walls. These were part of the extracted walls, right? And
They do that on purpose, or is that just?
No, it's aesthetic. I mean, they do that for, especially when you have window frames. It's much easier if you have this sort of beams of timber, right? So you can touch your frame directly, you know. And sometimes they use this also. There was such an abundance of timber back in the days. So sometimes in my office I have one. There are timber bricks. They would just put there. Why not? Why not? I mean, there's a lot of timber, right? So why not? And also, especially there's this joke, right? On Friday, you would see right at the end of the weekday, you will see your bricks that are coming a little bit wavy because the mason wants to go home. So they would used to use these timber beams, which are really long. Imagine a wall from here to there, right? So at every Friday they would put a timber beam to make sure that it would be straight. And it's actually what happened. And sometimes you have this in buildings. Well, I'll show you a few images, but they are everywhere. So yes, it's very practical, right? But if you don't know the history, then it's hard for you to make sense of it. No? It makes sense. It's a Friday. They were tired. So these are some of the walls that we got. And I mean, even from a practical perspective, you see there are one brick, two bricks. This is the load-bearing part, no? And this is the veneer. So they were trying to have as many leaves as possible to try and contrast the cold, no? Which makes sense. Nowadays, always we have a cavity here, right? The insulation. Back in the days, they didn't have that. So what is cool about this? These bricks are much stronger than the one that bear the load because inside they have silica. No? So they have a sort of a material that when they cook these bricks, they want to be less porous, so they are much more effective to screen against the weather. No? It makes sense. So these were not necessarily excellent bricks durability-wise, but they were covered, so it makes sense. So they are coupled with car parts. So scrap metal. So this are all metal. It can be steel, can be iron, I should say. It probably came from either machines or cars, and we find many of those, all different. But if it's an interesting learning process. So if you look at this wall, there was a timber beam right here, from this part to this part. Imagine the window was here, so it kind of makes sense that they have this anchorage point. So if you don't know this and you analyze this wall, assume that it's a normal wall, you would never guess that the deformation of capacity of this wall is so large. No? So that is why knowledge is so important. Ties that we have found, because literally we had to go there with a scanner, because we couldn't disassemble the walls because we want to test them. So went there with a scanner and non-destructively detected all these ties, all kind of ties. No? A lot of variation in there. Mostly iron, which kind of makes sense. But at least they have coupled the walls. No? So there was an attempt to make things working in a certain way. The bricks. So if you see the bricks, they're all curved because these are built with fabricated with traditional methods. No? Well, of course, we did all sorts of tests on those. It was a lot of fun. We did tests on samples, so you get the compressive strength of the assembly. Very important. And then I mentioned timber. So of course we had the beautiful timber that was in there. It looked very old, but whenever you you cut it, you would see that inside was perfect. And this performs exactly, actually even better than the modern timber that we have. This is a slow growth timber. Nowadays we use accelerated growth for our timber. It actually is structurally speaking, it's very bad for that. So excellent timber in there. If I'm showing you the results, of course, we had to make a few adjustments. This is the standard. It helps you to crush the wall 45 degrees incline. If we had to rotate our walls, it would have been a mess. So we had a sort of a compromise, something like this. And this is a little fun crushing this. But this is a test that we performed. The beam is right here. And you would see that if you apply the load here, the wall starts sliding at a certain point. So it will not crack diagonally, right? It will crack in this fashion. So from a sustainability climate change perspective, your envelope will crack less, right? And this is much more resilient than other types of walls. Right? The cracking pattern, all the different cracking patterns, it really depends on where the beam is, right? So the beam really dictates how the wall is behaving, which is kind of interesting. So if you know that, you would be able to sort of refine your assessment. So this is another test, similar test with a replicated mortar. Okay? So I told you that these mortars are so much stronger than the old ones. So look at what happened. It's very similar, right? And then these all collapsed. So current mortars are so strong that are explosive, no? And a big problem with respect to climate change adaptation that unfortunately nowadays it's very hard for us to formulate materials that are compatible with the ones that we had before. So this brings me to our next project. So I don't have a lot of time, but I'll try to give you an overview of what's going on. So you have seen all the characterization that we've done on those buildings. No? So we have a lot of data of how existing buildings here should behave environmentally and structurally. So we came up with an idea. So how we can try and repair them in a way that is affordable, that people can actually implement these solutions originally. And my main concern as well, I'm going to sort of bridge the gap from a structural perspective. I also want to bridge that gap thermally, so that it's a solution that is holistic. So this is one of the solutions, well, the solutions we came up with, the timber one, and then some grids that I'll explain in a second. So for the timber panels, we have used plywood and lumber that are at the end of their life. So you can literally find, at Home Depot and in these big retail stores. It's a modular retrofit, so you actually attach it on the walls, either internally or externally. And it's also thermal benefits. It would work in Montreal, it would not work in BC, of course, because it's meant for low seismicity. This again was a big project for us, so it was a lot of work to do in just 1 year, 2 years actually. This is the idea, no? So you have your timber panels, then you have insulation, and then you have your anchors, and so you can attach this locally to your wall. So of course, if you have a wall, then it's going to be covered by different panels all the way. If you have a building like the one that we have expected, you have your grid. So you try to sort of bring it up to code and you adapt it, environmentally and structurally. So you'll have something like this. Now, if it's a heritage building, you would retrofit from the inside. If it's a normal building, you may sort of apply this and then clad it. So it doesn't solve all the problems that are in the work, but it certainly helps bridging the gap between the code and the existing structure. The big sort of takeaway from this is that if you try and make this up to code, then you will not necessarily need to demolish this, right? This is the idea. So you have these panels that are attached, and this would be the thermal layer. And then you sort of seal it, and then apply it locally to the anchors. So a few images of, because we have tested all these solutions, now we have a bigger wall, but in general, it really helped. This is John, our technician, trying to get the anchors in. Was quite interesting, right? So you have an X sort of braces, you have boundary elements, and then you have your plywood. So we did a lot of analysis. So this is the thermal analysis, and this would be our structural analysis. And all the simulations, it's a big project. So when you sort of convey what is the effect of this retrofit structurally, the panel will be here. It's the same test as before. You remember the big collapse? So what you will not notice here maybe is that there is a sliding at the base. So a local cracking, non-explosive, the damage is reduced. So of course, if your envelope is less cracked, it's going to be more durable throughout the years, right? So in general, the displacement this would be the unreinforced case, this would be the reinforced case. So a lot of increase in terms of thermal capacity, and this would be the cracking pattern, the different differences in there. So in terms of thermally speaking, the retrofit. Was very efficient as well. So we got a lot of 4 times increment in the R value, which is a thermal transmittance. We use what is called a cool room, hot room. You have your panel in the middle. Then you will be able to see what is the heat transfer in there. So yeah, these tests were done at the University of Toronto. A lot of wires, there's not much to see. It's just a big box with the panel inside. But it was extremely good to see that the panel performed well. These are OSB panels, plywood panels on top of our masonry walls. Of course, we did a lot of simulations and so on and forth. The big picture would be to have them applied in different locations of the building. Now we're currently working on the upscaling of this technique. And the design process is a complex one. So every detail, it's very important. Slotted gap, because of course, if you have any existing buildings, you need to make sure that you have a little bit of flexibility in mounting the panels. So it's a lot of sort of thinking process that goes into that. right? And these are some of our mezzanines that are built in the wall. This would be some of the damage. So it's big scale walls. We aim to apply the panels. So if you stop by in McDonald's, we're going to test this next week probably. Caber, I've mentioned Caber, big facility, one of the biggest in the world actually. These are, you remember the hotbox that I showed you before? This is the biggest hotbox that there is around. So you put this panel, which would be 3 by 3 meters inside. You spray it. So we have simulated years of rain from Quebec City, and trying to see how it would perform. And the same applied for the moisture. And so we did all kinds of environmental tests there. Try and see what would be the durability of it. So not only that, there are other alternatives one can explore. Recycled plastic is one of that. Now, you're plastic, you say, oh my God, what's going on, right? But in general, there are some materials that are better than others that can prevent sort of crack forming. This material in particular is used for soil containment. So our principle is, let's see if we can find in other sectors, in other fields, material that are performing in a certain way to try and confine cracking and try to have insulation into that as well. This sort of the interesting thing about this project is that we're using an environmental chamber, and inside the environmental chamber, we're doing the test. So of course, this could perform well in California. But what if it's exposed to minus 40? It's going to change a lot. No? And so we want to make sure that everything is local. Because if you try to do this, then you're adapting your solution to the current climate. No? Just an example. You have mortar layers, and then you have your geogrid, your wall. So there's a lot of testing going on a number of directions. And this is what I'm saying. It changes. No? This thing, which is made of plastic, will probably become more ductile whenever the heat increases. And the same applies for this, which is a fiberglass fiber. So this would be our environmental chamber. It's small, right? So you have one brick, mortar, and then you have your grid. You try to sort of elongate it. You'll have different responses. It changes with temperature, but you need to assess those to make sure that your building is, or at least your structural detail is adapted. The more the temperature decreases, the more this becomes brittle, and it fails before. So it makes a lot of sense to sort of adapt your solution for that. Another example, right? So this would be our current setup in the environmental chamber: brick, mortar, and then you tension it under different types of. It breaks, so it's a lot of fun. It doesn't explode, but still, it's you'll see damage in there. No, and this is an example of fiberglass, which is a different fiber. So in general, this is all. It's a big overview in a very short time. So of course, you need to be creative in the way you do things, and that's John's pickup, our technician. So we have fun. Thank you.